Welcome back. In the roadmap video, I showed you the full path to becoming an ML engineer. Today we start with Phase 1, Data Pre-Processing. Before any algorithm ever sees your data, that data has to be cleaned, split, scaled, and encoded. In this video, I'll walk you through every concept in this phase with visuals and real code, so by the end, you can take a raw, messy dataset and make it model ready. Let's get into it. Dataset, features, and labels. Let's start with the vocabulary because you'll hear these words in every single ML video from now on. This table here, the whole thing is your dataset. Every row is one sample, one data point. The columns you use to make a prediction, age, income, city, these are your features. And this last column, bought the thing you're actually trying to predict, that's your label or target. So dataset is the table, features are the inputs, label is the answer you're training the model to give. Train/validation/test split. Now here's a rule you must never break. Never train and test your model on the same data. If you do, you have no idea if it actually learned anything or just memorized the answers. So we split our dataset into 3 parts. 60% becomes the training set. This is what the model actually learns from. 20% becomes the validation set. We use this while we're still tuning the model, checking if it's overfitting. And the last 20% is the test set. We touch this only once right at the end to get an honest final score. Here's the code. Missing values. Real-world data is messy. Look at this table. We've got a missing age and a missing income. These show up as NDNAN. Models cannot handle blanks, so you've got 2 choices. Drop the rows that have missing values or impute them, fill them in with something sensible, like the mean, median, or most frequent value. Here's both approaches in code. Drop nay removes any row with a missing value, or if you don't want to lose data, simple imputer with strategy equals mean will fill in the gaps using the column average. Duplicate values, next up, duplicates. Look at rows 2 and 3 here. Same age, same city, exact duplicates. Why does this matter? Because duplicate rows quietly bias your model. It starts treating that repeated pattern as more important than it actually is. The fix is simple. df.duplicated parens dot sum parens tells you how many duplicates exist, and drop underscore duplicates parens removes them, keeping just the first occurrence. Outliers. Now outliers, these are data points that sit way outside the normal range. Look at this box plot. Most of our data sits comfortably inside this box. But these 2 pink points way out here, those are outliers. Why do they matter? They can drag your mean way off, distort your scaling, and confuse your model's learned weights. The most common way to catch them is the IQR method interquartile range. We calculate Q1 and Q3, find the range between them, and anything outside 1.5 times that range above or below gets flagged and removed. Feature scaling. Here's a problem. Age might range from 18 to 60, but income ranges from 20,000 to 200,000. Any model that uses distance or gradients is going to get completely dominated by the income column just because the numbers are bigger, not because it's actually more important. That's where feature scaling comes in, and there are 2 main techniques. Normalization, or min-max scaling, squashes everything into a 0 to 1 range. Great for neural networks or image data, but sensitive to outliers. Standardization, or z-score scaling, centers your data around a mean of 0 with a standard deviation of 1. This is the go-to for things like linear regression, SVM, and PCA, especially when your data has outliers or isn't bounded. Both are one line of code with scikit-learn. min-max scalar or standard scalar, then fit transform. Encoding categorical data models only understand numbers, not text. So if you've got a column like city, with values like Lahore, Karachi, Islamabad, you need to encode it. There are three main approaches, and which one you pick actually matters. 1. Hot encoding is for categories with no natural order like city. It creates a separate 0/1 column for each category so the model doesn't accidentally think Karachi is bigger than Lahore. Label encoding just assigns each category a number 0, 1, 2. This is mainly safe for your target/label column, but risky for input features because it implies an order that might not exist. Ordinal encoding is for categories that genuinely do have order like small, medium, large. Here the numbers 0, 1, 2 actually mean something. Feature engineering and feature selection. Two more important terms that sound similar but do opposite jobs. Feature engineering is about creating new, more useful features from what you already have. Classic example. You don't really need someone's birth date, you need their age. So you engineer a new age feature from it. You could also combine columns like income divided by family size to get something more meaningful. Feature selection is the opposite. It's about removing features that don't actually help. Fewer, more relevant features mean faster training and less overfitting. Select K Best is a quick way to automatically keep just the top K most useful features. Data leakage. This one trips up a lot of beginners, so pay attention. Data leakage happens when information from outside your training data sneaks into the training process, and it gives you a model that looks amazing in testing, but falls apart in the real world. Here's the classic mistake: scaling your entire dataset, including the test set, before splitting. That means your scaler has already seen statistics from the test set, which is supposed to be unseen. The right way? Split first, then fit your scaler only on the training data and apply that same scaler to the test data. The test set stays completely untouched until the very end. Data imbalance and SMOTE. Last topic for this phase: imbalance. Imagine a fraud detection dataset where 95% of transactions are not fraud and only 5% are fraud. If your model just predicts not fraud every single time, it gets 95% accuracy and is completely useless. So how do we fix this? You can oversample the minority class, or undersample the majority use class weights, or use a technique called SMOTE, synthetic minority oversampling technique. SMOTE doesn't just copy-paste existing minority samples, it actually generates new synthetic data points by interpolating between existing minority class neighbors. One line of code with the Imbalance library and your classes are balanced. Recap. And that's phase 1 complete. Let's quickly recap everything we covered. Dataset, features, and labels, the basic vocabulary. Train test validation split for honest evaluation. Missing values, duplicates, and outliers, the cleaning trio. Scaling and encoding to get our data into the right shape. Feature engineering and selection to keep only what matters. And finally, 2 pitfalls to avoid: data leakage and class imbalance, solved with SMOTE. If this helped, smash that like button and subscribe. In the next video, we move on to phase 2, machine learning basics, where we'll cover supervised, unsupervised, and reinforcement learning, plus how to actually evaluate a model properly. See you in the next one.